Okay, as promised, this is the video for a cubic regression where you need to come up with the points. And so this is on page 54 in your notes. All right, so um, basically, whenever you deal with volume, any question regarding volume, you're going to end up with a cubic regression. All right, and there's a little bit of a nuance there, which I will show you in a bit. Because a cubic regression can only partially model. And obviously there's some restrictions there we need to put in place. So anyways, you have a rectangular sheet of cardboard. And the idea is, right, what dimensions should the squares have to maximize the volume? Okay, so in a sense, we want to determine the dimension of these squares, and obviously they all have to be the same, so that when we fold this up, right, we actually end up with a box that will have length, width, and height. Okay, so if you look at this, we have this piece of cardboard that is 40, right? We know that the length is 40 centimeters, and the width is 15 centimeters. Right, so 40 by 15 is the cardboard, and we will assign x to these squares here. It's an x by x square, and they're all the same. So we go around like that. And really, if we look at the box itself, the resulting box after cutting out these corners, right, we would have the length here would actually be from here to here would be 40 minus x and minus another x, because you'd be cutting both of those out. So it ends up being 40 minus 2x. This is the length of the box. Okay. The width of the box, right? You would essentially start with 15 and subtract 2x as well. So this 15 minus 2x is the width of the box. Okay. And so we have our length, width, our length, and obviously the height. The height of the box would be determined by the dimensions of those cutouts, right? Because if you fold this up, right? If you fold this little lip, the width of this lip is going to essentially be the height of the box. So we would have to agree that x, whenever we find it, that would determine the height of the box. Okay. All right, so let's go ahead and determine a cubic regression that would model this scenario and allow us to figure out the dimensions that would actually maximize the volume, because there's a way to do that. And what you need to do here is basically we start with our height. Our height is our ultimate independent variable, right? Independent. And so everything else depends on what we make the height to be. So I will actually tell you that it doesn't matter what x values you pick. It's just like the fencing question when we did the quadratic in grade 11 applied, which I will also do. But really, this is, if you let x be the height of that box be 2, 4, 6, 8, you kind of want to go a little bit, you kind of want to look out what are the sizes, what is the cardboard measure, 40 by 15, right? And so kind of keep it within reason, even though it doesn't matter. You could pick 100, 200, 300, 400, you could pick whatever you want, but you would end up with a negative volume, which you know that you cannot have a negative volume in the real world, but it still works for us because the calculator will take those negative values and still kind of plot our cubic that way. And then we'll just later on have to kind of restrict it in terms of the domain and range. Anyway, so remember that the length is 40 minus 2x, and the width is 50 minus 2x. So the height, length, width, and the volume is just, volume is length times width times height, right? It's multiplying all three of these. So for the length here, 40 minus 2 times 2, like if the height were to be 2, so that would be 36. I will do all the lengths here. 40 minus 2 times 4, that would be 32 because it's 40 minus 8, right? 40 minus 2 times 6, that would be 28 because it's 40 minus 12, right? And so if you're not sure, just use your calculator, right? You can go 40 minus 2 times 6. There you go, right? This is 40 minus 2 times 8, and that's 24. Okay, so I do all the lengths so I don't kind of jump back and forth and mix it up. It's always 40 minus 2 times whatever the height is in that scenario. And so let's go over to another. So basically what you're doing is giving the calculator enough to model it, and the calculator essentially shows you all possible combinations and the corresponding volumes, okay? But you need a minimum of 4 points if it's a cubic. Remember, degree plus 1, that's the number of points you need. 15 minus 2 times 2, right, that'd be 11. 15 minus 2 times 4, that'd be 7, right? 15 minus 8. 15 minus 2 times 6, that would be 3. And here is the negative here. 50 minus 2 times 8, that's 50 minus 16, that's negative 1. That's okay. Just put it in. I actually did that on purpose. And then we get our volume. So 2 times 36 times 11, right? And we'll figure that out. And then it's 4 times 32 times 7. And then it's 6 times 28 times 3. And then it's 8 times 24 times negative 1. So you're going to get a negative answer here because you have only one negative in there. And I will tell you, right, that we will make this our L1 and the volume our L2, okay? So these are still part of, these still play a part because you need them to figure out the volume. So let's go ahead and type that in. I will clear everything. So it's 2, 4, 6, 8. And then we have the volumes, right? So 2 times 36 times 11, that's 792. 4 times 32 times 7, that's 896. 6 times 28 times 3, that's 504. And then it's 8 times 24 times negative 1, right? And that's negative 192, right? So that's your chart. You have that filled in. And now they're asking us, using a cubic regression, they shouldn't have to tell you that, but when it's volume, right? Because if it's volume, you know it's cubic. So to determine the squares that should be removed to make the box with the maximum volume. So we'll figure that out. So we're going to go stat. Let's write that down first. Stat, calc, cubic reg. Okay. So we're going to go stat, calc, cubic regression. Second one, second two, comma, alpha trace gets you to y1 really quickly. And there you have it. Hit enter. And you go y is equal to 4x cubed minus 110x squared plus 600x. And this is 0. And remember, if it's anything with an e to the negative, what have you, we consider that 0. We don't include that. Okay. So there you have it. You have your quadratic. And we want to find out the dimensions of the squares that would maximize our volume. Because remember, right now, this gives you the height of the box and the corresponding volume. Okay, and I have to say that because everything is in centimeters, in this particular case up here, every single one of these is in centimeters cubed. Okay, remember that. And so we'll figure that out. So we graph it, and here's where you need to watch out. So I'm going to go zoom 9, and it doesn't work for me because oh, I'm just going to pause the video here. All right, so I turn on plot 1, and now it's going to work for me. There it is. So, and I'm going to adjust my min a little bit, also my max, and I'm going to go to 50 there. I don't need, I'm going to check what this looks like. And there's your quadratic. I need to see a little bit more here to get the min, even though I'll tell you that it doesn't really matter. I'm going to go negative 1,000. Oh, I need to go lower. Negative 2,500. There we go. So here's where it gets a little controversial, and I'm not graphing it here, but really, remember this is the height of the box, right? The height of the box, that's the variable that we graph here, and this is your volume. So as the height increases, the volume increases to a certain point where now when you make it taller, then this height right here, which you're going to find out right away, the box, the other dimensions start to shrink, right? So it becomes, yeah, it becomes taller, but it's really getting narrower or shorter, right? And so then it goes back down. And so the maximum, the height where our domain would stop right about there, where you go back to 0. Because here, this is a negative volume. We can't have that. Negative volume. And you'll find out that this x-intercept out here doesn't apply. Here is why. Watch this. I'm going to find that second trace 5. And where's my cursor? So I'm going to jump. Oh, there it is. Enter, enter, enter. And that's 20, 0, a height of 20. Think about it, if you look at it, a height of 20, like if this were to be 20 and 20 here, right, that's impossible, right? You only have 15 to go with. So it's like 15 minus 20 minus 20, that will give you a negative. So it's impossible. That doesn't work. Same here. If this is 20 and that's 20, then it's 40 minus 2 times 20, which is 0, right? So you'll find that every time, in fact, out here, anything past the first x-intercept, right, as it goes up, comes back down, anything past there, it's not applicable. And I'll show you that x-intercept, so that's 7.5, right, a height of 7.5, which 15 minus 7.5 minus 7.5, that would get you straight to 0, right? And so yes, we do see that at that point the box has a volume of 0. Okay, but that's the biggest height you can have that possible. After that, we don't accept it anymore. All right, lots of interruptions here. So let's find the maximum height, right? So the only really highest point is here. Like this goes in indefinitely, but within our domain and range, that's our highest. So second trace 5, nope, sorry. Second trace 4 to get the max. So we're gonna hit enter, enter, enter again. So that's 3.339259.3. Okay, so second trace max, and we have 3.33.925.93. Okay, so sorry you can't see that, but this is a height, right? Squares. Okay, I will say this: squares with side length of 3.33 meters will result in a box with maximum volume of 925, 93. And we are in centimeters cubed, right? So we found the height of the box, which is essentially the side lengths of the squares that we're going to remove from that sheet of cardboard, right? We're going to cut these out at 3.33 and 3.33 this way, and then fold it, and that'll be the box with the greatest volume, given our dimensions, right? State the domain and range. For domain, we're going to go from 0 to 7.5, because I showed you that the first x-intercept here was 7.5, right? So it goes from 0 to 7.5 for the height, okay? And the range would be from 0 to 925.93, right? That's our highest volume. So there we go. I wouldn't mind going through the graph with you, right? Graph. So I know it's going to be longer than I promised, the 15 minutes, right? But let's go over here. Maybe I will just show you what the graph looks like. Okay, so you can do that on page 55. But I essentially treated it at first as just a cubic function. And so I found all the x-intercepts, and I used the keystrokes. I found the max that I already did before. I found the min, which is here, right? Like these are always, you need to have the max, the min, and the x-intercepts as well as your y-intercepts. You have volume in centimeters cubed, you have height in centimeters, and I drew my x and y axis, and I spaced it out equally. And because my lowest went down to 2,250, I needed to make sure that is included, right? So my y-axis is actually going up by 500. And this is here, I went all the way to 20. And so you have your max and your min, there you go. But after this point here, right, there's no width, right? This is 7.50. And so we kind of like ignore this part right here. It would just be this little, which kind of looks like a parabola, right? But a cubic function models it best, okay? Because it does have a little bit of a different characteristic. And here's my domain and range again. And I went one step further. What dimensions, if it ever asks you what dimensions will yield the maximum volume, right? Again, you go by this. And so this is one of the dimensions, which is the height. So the height is that, but the width is 15 minus 2 times the height. The length is equal to 40 minus 2 times the height. So these three dimensions here will give you the maximum volume of that. And really, in theory, you should be able to multiply all three and get roughly that answer. We're not quite getting it, and that has to do with the decimals, right? Like if you use more decimals in every single scenario, it would work out to be very close to that, okay? I don't know if 834, 33. Oh, I put 84 there, hold on. It's supposed to be 34, right? 34, not 84. And then we're closer, 925.93, there you go. So there we go. This is basically it. And then tomorrow I'll do the fencing yet for the quadratic. And then we're basically ready. Thanks.